Well, welcome everybody. For those of you who don't know me, I'm Samuel Singer. I'm the founder and executive director of Wyoming Stargazing. If you wouldn't mind muting yourself just to begin, we'll let Mike kind of introduce what we're going to be doing tonight. And if you have any questions throughout the evening, feel free to either type them in the chat option, or you can just unmute yourself and ask your question, and we'll do our best to answer it for you. We're going to go for about an hour tonight. We got a lot of fun things to show you. And so, yeah, please ask all the questions you have, and I think we'll have a real fun time. Mike, it's all yours.
Okay. All right. Just to, we're going to focus on the comet a little later, but this is a picture I took last night. You saw some of Samuel's pictures, but yeah, this is a picture not taken with any of these big telescopes. With a regular camera and 170mm lens. But anyway, this is something that anyone who's up here in Jackson Hole can do and should have and should get out there and do it, because it's maybe a once in a lifetime thing to get a comet with this amazing tail. Anyway, okay, so we're gonna come back and show you some live pictures of the comet a little later, but this is one from last night. Okay, so now we're going to, I'm going to go back to share, do a different share. Okay, so this is my control system for my telescope. And right now the telescope is just sort of parking there. And now we're going to look at the first object of the night, which is going to be the M57, which is called the Ring Nebula. And it's a nebula that's a leftover. I'm echoing in my computer here. Well, I'll try to avoid it. Anyway, it's a nebula that's left over, but let me get it on the screen and then we'll talk about it. So first thing I'm going to do is point to it. It's called M57. I'm going to sit fine, and there it is, right there. Oh boy, now it's going to be tricky. All right, I'm going to hit go to. So this is a computer-controlled telescope. So I'm doing all of this from the comfort of my home, although my telescope is only 200 feet away from me. But that's not a problem in the summer like this, but in the winter, it's awfully nice to be inside. Okay. Now I'm going to tell the telescope to move to that object, and it's now moving. And you can see it moving.
We're having a couple of problems here. So I'm going to quit this for a second.
Okay. Now it's tracking. Okay, we're going to change this screen to a different screen. Share screen. We're going to go to the this screen, which is the screen that controls the camera, and we're going to take a picture. So I'm going to take a single picture. Maybe, no, I don't need, now 10 seconds. Okay.
You see, because we don't usually have the sound here.
So what you're looking at is,
Mike, go ahead and unmute yourself. We had some background noise.
okay. All right, I've unmuted myself. So there it is. So that's M57. And this is what is called a planetary nebula. It's a leftover, it's a leftover remnant of a star, much like our sun. And when a sun, what's going on right now with our sun, it's burning as hydrogen and it's creating helium. And turns out there's a little bit of difference in mass between the hydrogen and the helium, and the difference is energy, and that's E equals mc squared. So that's why the sun produces light. It's conducing hydrogen into helium. And well, what happens is the sun is going to do that for a while, and once it uses up all the hydrogen, which is going to be in a couple of billion years, it's going to start. The flames are going to go out momentarily. Gravity is going to take over, and it's going to squeeze itself really hard. It's going to squeeze the leftover helium enough that it's actually going to create a new nuclear reaction, and the helium is going to convert helium into carbon. And then what's going to happen is after all the helium is gone, it's going to heat up the carbon again, but it's not going to get hot enough to start another nuclear reaction, and the sun is going to burn out. And what's going to happen is gradually it's going to expand into what's called a planetary nebula. Now, it's not really a nebula, it's not a planet, but the astronomers call it a planetary nebula because it's round and it's shaped like a planet. Anyway, so what you're looking at here is the remnant of a star like the sun. The very center of this is the leftover star itself. It's called a white dwarf, and all it is just really super hot carbon. It's not a nuclear reaction anymore. It's just carbon gradually cooling off. And anyway, so this is M57. I've been photographing this myself for the last maybe 3 weeks, and there's a lot more stuff out here around it that you can't see in this picture, but I can see in this image, but I can see in a picture, and I'll be sharing that with folks in the next couple of weeks or so. But anyway, so this is a planetary nebula, and it's we're going to see, we're going to move on from this to another planetary nebula, but so we'll have 2 of those.
Yeah, and the nice thing about the next one is that we get to see it from a different perspective. Mike was mentioning how the misnomer in the name of this object, the planetary part, astronomers saw these circular shapes in the sky and they thought they were planets forming. We now know they're sun-like stars dying, but it all depends on the perspective you're seeing it. The actual shape of these planetary nebula are actually kind of like hourglass shapes. The gases from the dying stars get expelled from the poles of the star, and then they spread out as they go. So this next object we're going to show you, we actually see it from a different perspective, 90 degrees in difference in the orientation from which we're seeing this one. And you can actually see a little bit of that hourglass shape. This next one's called the Dumbbell Nebula. So same type of shape, a dumbbell, as opposed to this object, the Ring Nebula, where we're basically looking down through one end of the hourglass shape. So we just see a bright outer ring.
Okay. Unfortunately, this one's going to take, the telescope's going to have to slew around, but I'll deal with that. All right.
So this object here, oh, go ahead, Mike.
By the way, doing the next objects, because now the telescope is flopping, so it'll take us 30 seconds or so to get around to finding this next guy here.
Yeah. So this one's about 2,300 light years away, which is still relatively close compared to the galaxies we'll look at later on tonight. But 2,300 light years means we're collecting light that left that object 2,300 years ago. So we're seeing it as it looked 2,300 years in the past. This next object, the Dumbbell Nebula, is a little bit closer. It's just around 1,200 light years away compared to the 2,300 of this one. Both these objects are roughly a light year in diameter. So across the diameter of that ring you're seeing there is about 6 trillion miles. So the solar system, including our Oort cloud, would fit snugly inside that ring. So that gives you an idea of how big of an object we're looking at here. 6 trillion
Okay, so I'm now
miles in
going to hit
diameter.
this. I'm now going to hit the start menu here. We're going to take a different picture. The telescope, since we've been talking, has moved to the Ring Nebula, from the ring to what's called the Dumbbell Nebula. And here's the Dumbbell Nebula, which I'm going to unzoom. And we're going to brighten this up a little bit. So there it is. Maybe
Yeah, so you can really see how it's narrow in the center and then it bulges out on either end.
yeah, so there it is. And the leftover star here is right there. And it's called a dumbbell because these areas are a little brighter out here. And so it kind of has a dumbbell shape if you follow this curve. So this is a very beautiful in color. This is a fairly green, and so it's a mix of and these areas out here are red, and what it is the leftover elements. So the green part is oxygen, the leftover oxygen from the star, and the red part is leftover hydrogen, and hydrogen emits in the red.
And the texture we can see in the gas there is pretty awesome.
Yeah, it's very nice. As one benefit, I mean, this was just a 10-second exposure, but you can't see, as nice as it is to look at these things through an eyepiece, you can't see this level of detail through an eyepiece. We're seeing even a 10-second exposure that's got more, it really shows more detail than you can with your eye through an eyepiece. Now, that's not true for everything we're going to see tonight, but for these nebulas, it is.
Yeah, even through a 25-inch telescope, this just looks like a little gray smudge looking with just the naked eye.
Okay. Yeah, I actually, last week, by the way, Samuel, I photographed, I saved these photographs, so I have these photographs of the.
Oh, great.
So I can send them to you and we can. Okay, so we'll now move on. Since we're off the page there a little bit to the left, let me, I guess we'll move on to, what was next on what we're going to go do? Some of the galaxies, or we're going to go on to
some of the emission nebulas. Either
okay,
the,
so we'll make a big jump in the space. I'm going to change this, and I'll show you what's going to go on here because we're going to change our location in the sky big time here. Okay, so here we are. I'm going to swing this around. Okay, there's the North Star right there, the North South celestial pole. We're way up here in the northwest at the moment. This whole thing down here, this bright smear, is the Milky Way, and which is now visible, and in the evening sky. And there's a ton of beautiful stuff in the Milky Way, and we're going to start looking at it. We're going to look at some what are called emission nebulas in the Milky Way, and these are some of the real showpieces of the Milky Way, and you can only see these in the summer. So we're going to be looking actually fairly close to the direction of the center of our galaxy. And so I guess we'll start with maybe the most famous of these, which is M16, called the Eagle Nebula. But there's a very famous Hubble photograph of called the Pillars of Creation, which I'll show you what that looks like, at least through my 20-inch telescope. So now I'm going to hit find, and you can see it. So there, we were looking up in the northeast. We're now going to go down to here, which is south and west of where we were just looking. The telescope, though, is going to have to swing all the way around to come around here. So now I'm going to say for it to go, and it's going to go, and you'll actually see it doing its thing. It's going to actually flop around, going all the way up to the North Celestial Pole, swing through the pole, and then come down to on the other side, and we'll be looking at, and we'll stay, I think the rest of the objects we're going to look at are going to stay with the telescope on the east side looking west.
One of these days, Mike, we should shoot a little video of your telescope flopping so we can show it to everybody.
Yeah, it is interesting because it's swinging around pretty dramatically at the moment, and you can only see it what it's doing in the sky here, but it's whipping around. That's one of the great things about having an observatory, because the telescope is permanently mounted, and all I have to do is turn it on and tell the computer to point, and it does that. Back in the day, before I had this, I had to wheel my telescope and mount and everything out of my garage, and then align it to the stars before I could do any of this. So this is great. Okay, so I've done that. It's now pointing at this. Now we're going to change the screen back to the camera screen, and we'll now tell it to take a picture. Now I'm going to tell it to take a 20-second picture this time. Nope, not 30, just 20. And we're going to. So this is called an emission nebula. What that means is that it's emitting light, and it's emitting light because stars in the area are exciting the gases, and the gases, which in this case consist of mostly mostly of hydrogen and oxygen. I'm going to darken this a little bit so you can see it.
It was a lot better just before you did that, Mike.
You liked it better? Okay.
Yeah.
You know, what I see and what you see are different. So
yeah,
you tell me when you think it's
right
best.
there. Yeah, right there.
Right
Yeah.
there. Okay.
Mhm.
Yeah, it's too bright on my screen, but it's better for you folks. So what's going on here is you see that this is a loose cluster of stars. It's called an open cluster. It is in this very same area. One of the weird things about looking at pictures like this is that a lot of these stars could be at any distance from you, and only some of them are in the same location as this nebula. You can't. One of the big mysteries of all of this was over the last 100 years is to measure distance in the universe, and but in this case, this cluster is actually causing ultraviolet light to excite the gases in this nebula, and the gases in this nebula are being excited by this ultraviolet light and re-emitting the light. And so these clouds are the emission nebula, and it's mostly hydrogen gas, which is the dominant element in the universe. 75% of everything in the universe is hydrogen. And it's re-emitting, it's getting excited, it's being elevated to an higher energy state and re-emitting it. Now, I should say something about nebulas in general. All the stars in the universe were once created out of nebulas. They are gas and dust clouds where gravity compressed the gas and dust to a point, in particular hydrogen gas, to a point that it actually heats it up to 15 million degrees Kelvin. And that causes a nuclear reaction to start. So all the stars in the universe, we started the universe at the Big Bang with no stars, only hydrogen gas, and little disturbances caused by during the Big Bang resulted in these little disturbances caused gravity to compress the gas in various places, and stars started forming. And guess what would happen if the stars didn't form? We wouldn't be here, because everything other than hydrogen and helium were created by the stars. So these nebulas are star factories. That's what we're looking at. Now this guy is called the Eagle Nebula because some people thought that these wings here look like an eagle, but I think this looks like a woman's head to me, and if you see some of my actual pictures, it's a little more dramatic. But this little structure down here, by the way, is called the Pillars of Creation, and I can zoom it in a bit more, and you might recognize it if you've seen the Hubble images of this, but this is called the Pillars of Creation.
So to give you an idea of the scale we're looking at here, those little pillars that Mike just brought his cursor around are several light years long. The entire nebula is about 50 light years by 70 light years, so 50 solar systems tall by 70 solar systems wide, and those tiny little pillars are several solar systems, 2 or 3 light years long. So this is a huge, huge object that's giving birth to thousands of stars.
Yeah,
And,
this whole thing in the sky, since I took it with my 20-inch telescope, is about the size of the moon in the sky. So these are large objects visually in the sky. Unlike the planets, which look like stars to you, well, these are way bigger than any of the stars, but you can't see these because they're so diffuse, and it takes a camera or a telescope to bring them out.
Yeah, and this one's quite a bit farther away than the last couple planetary nebula we looked at. This Emission Nebula is about 6,500 light years away, so we're moving farther away out into space now.
Yeah, and it's in the direction from where the sun is in our Milky Way. It's in the direction of the center of our galaxy. So we're looking from where we are towards the sun is about a quarter of the way outside. The Milky Way is about 100,000 light years in diameter. We're about 25,000 light years from the center, and we're now looking towards the center of the galaxy. Okay, we're going to look at another one that's right next to this guy. There's 4 of these. They're very famous, and they're right next to each other. I'm not going to change the screen. I'm just going to go to it. It won't take long for the telescope to get there. We'll go to M17, which is right next to this guy. And I'll say, fine, go, is going, it's there. I'm just going to go back, take a picture, and we'll take a picture of M17, which is another emission nebula, very famous.
The Swan Nebula.
Right, doesn't look much like a swan. I'll tell you what I think it looks like when you see it.
Well, you know, when you look through a telescope, you actually can see the swan.
Oh, okay.
There's a real distinct swan shape. Actually, I can point it out to folks. You can see part of it here. The really bright area, you can imagine a swan's head kind of arcing up to the left, and then its body is that big long rectangle. So it's kind of swimming at a 45-degree angle up to the left.
Yeah,
That's the swan.
I think I want to change this. We're blowing out the detail in part of it.
Yeah, you can see the swan actually a little bit better there.
Okay, so what do you think? Where do you think the swan is in this case?
So her body is the long, bright kind of rectangle shape, but her head is up above it, right there. Yeah.
Okay.
And so she's swimming up to the left. Her tail feathers are at the bottom right, and she's swimming up to the left.
I always thought this looked more like a fish to me. You see, this, yeah, okay, so I thought this to me looks like a fish, not a swan, but that's okay. All right. Okay. Yeah, but this again is another emission nebula, and the Milky Way is just filled with gas and dust. And what we're looking at, if you've ever seen a picture or a sketch or a diagram of the Milky Way, it's a disk that's thin, and what we're looking in this case is along the axis of the disk. So we're looking at the densest part of the Milky Way and where all this gas and dust are. Okay, so we're going to now move on to, let's see, yeah, it's 10:53. All right, so we're going to now move on to a couple more of these guys that are in the same general area. So we'll look at something called the Lagoon Nebula, which is a little bit further south from here. Now
While we're moving to that, Michael, just answer one of the questions we have in the chat. Just a clarification between the difference between galaxies and nebulae. So nebulae are these huge clouds of gas, several light years to dozens of light years across, that are the birthplaces of stars in the case of Emission Nebula, and the death throes of stars in the case of Planetary Nebula. But they're tiny compared to the size of galaxies. Galaxies are the collection of hundreds of billions to even hundreds of trillions of stars, all orbiting around a central point, typically occupied by a supermassive black hole. And so the scale of galaxies is several thousand orders of magnitude larger than these nebulae. So there are thousands or even hundreds of thousands or millions of nebulae within galaxies. The Milky Way is no exception to that. So
yeah,
go ahead, Mike.
No, I was just going to say, all of these objects that we've looked at so far tonight are all in the Milky Way galaxy. And we're going to show you in a few minutes a totally different galaxy, which has its own set of nebula and what have you. So, so anyway, okay. So we're now looking at it's called Messier 8, which is I guess I like that previous picture better. It was a little bigger.
Yeah, this is the Lagoon Nebula, right?
Yeah, this is the Lagoon Nebula, and it sort of looks like a lagoon. It's a big circle here, and you see the star cluster down here. This is what's causing all this gas and dust to emit light. So these are stars that are emitting ultraviolet light, which is causing the hydrogen and oxygen and sulfur gas in these clouds to be excited, and then they re-emit the light at a characteristic wavelength. And hydrogen emits in the red, oxygen emits in the blue, the green blue. Anyway, so that's what we're looking at here. So this is called the Lagoon Nebula. And I'm changing the brightness so you can I won't blow. It's dim. The outer parts are dimmer now. One of the tricky parts of taking pictures of these things is that they vary in brightness a lot, and the center parts, some of these are very bright, but you see I've changed in the brightness, but I've now blown out the detail. You can't see the detail in the center, but you can see the outer clouds more clearly. And so making pictures out of this kind of stuff requires you to try to get a picture that doesn't blow out this detail, but shows all of this detail at the same time. Okay, so that's, and we have one more to go in this area, another Emission Nebula, which is right next door to this one. My 6-inch telescope, I have 3 telescopes in my observatory. We're using a 20-inch telescope right now. When we start looking at the comet, we're going to use my 6-inch telescope. But a 6-inch telescope can put this nebula and the next one we're going to see in the same image. But the 20-inch telescope, what these are is, unlike your normal camera where you put a telephoto lens on the camera, what you do here is you put totally different cameras on different telescopes, and that's the telephoto. But it's not like you don't put a different lens on the camera. You put a different camera on the telescope. So anyway,
so the telescope kind of becomes the lens.
Yeah, the telescope is the lens of the camera. But yeah, you don't just snap one on to a camera and take it off and put another one on. It's totally different. All right, so we've done that. We're going to make another quick change. We're going
Maybe
to
in the
go to
interest
something.
of time, Mike, we should go on to some globular clusters since
Okay,
we're
so we
kinda
don't
halfway there.
You want to pass M20? All right.
I think so, yeah.
Okay, so we'll look at M22 then, which is right down in the same neighborhood, which is a globular cluster. And yeah, you can't see the screen, but I will now take a picture of it. Okay, so we'll take this won't take a 20-second exposure. I'm going to take a 10-second exposure. Yeah, it's about 11 o'clock right now.
So now we're going to look at a totally different type of object. We're moving on to some globular clusters.
Oh, nope. What happened here? I
The
didn't tell it to
telescope
move.
moved.
I didn't tell the telescope to move.
Still looking at a nebula.
Yeah, there it goes. Okay, now it's moving. All right, gotcha. Okay, now I'll have to take that picture again. Okay.
There we go.
Yeah. So what's the best? Yeah, I'll change the brightness a little bit. This allows you to see the center detail, but maybe you'll see more of the overall if I brighten it up like
Yeah,
this.
definitely.
Okay. Yeah, so this is even a different, this is fairly close to this object in direction, but it's actually in a different part. It's located in the halo of our nebula, which is in the bubble. And what this is these stars are extremely old. This once was a nebula, but all these stars were created in this nebula. And but the gas, all the gas has been used up or blown away. And so all you're left with these very old stars, most of which are about 10 billion years old, which is about the age of our universe. I mean, it's within shooting distance of where the universe is 14 billion. Most of these stars are 10 billion years old. And these are globular clusters, which means there are some of these clusters that have as many as 100,000 to 1 million stars. I don't remember how many this one has, but a lot.
Yeah, I think it's a couple 100,000.
Yeah.
Yeah,
And
so
the
these
sun.
oh, go ahead.
Go ahead, Sam.
No. I was just going to say that these huge clusters are kind of like the precursors to larger galaxies. These objects existed before the spiral galaxies like the Milky Way, but got captured by the gravitational fields of big spiral galaxies, which is why they don't hang out in the plane of the galaxy where most of the stars are, but as Mike mentioned, up in the upper and lower halos of galaxies, up above and down below the disks where most of the stars are.
Yeah, this cluster of stars is about the same age as the Milky Way galaxy itself, which is, the estimates are the Milky Way galaxy formed 10 billion years ago. And all these stars are 10. So these stars really were older and than most of the stars in the rest of the Milky Way. And we're going to look at a couple more of these things. The sun, interestingly enough, could not have been formed in a cluster like this, because if the sun was in a cluster like this, it would still be there, and there would be millions of others, or hundreds of thousands, tens of thousands of other stars very close to it. We have never had a stable environment for our solar system to exist because of all the other stars. So the sun was undoubtedly formed in a nebula, because all stars are, but probably in a much looser group of stars, an open cluster, like the clusters we are looking at in the previous nebula, which didn't look like this at all. You could see the finite number of stars in that cluster. And those are called open clusters. The sun was undoubtedly formed in an open cluster like one of those. And over the eons of rotating around the Milky Way, it takes about the sun, our sun about 250 million years to make one rotation around the Milky Way, it probably split away from its sister and brother stars and is no longer in a cluster at all of any type. It's all by itself. Okay, there's another one that's in the same general area. It's called M4. We could take a quick look at that. Then we'll move on to the most famous of the clusters.
Well, so Mike, we got a question about the little 3D graph in the camera control that shows the illumination of the object.
Oh yes.
You want to talk about that for a little bit while we're moving to this next object?
Yeah, that's called a histogram, and it's this is if you can see these if you have a single lens reflex camera, the camera will show you a similar diagram. It shows you what the light is. So this is telling us where the light is. So it says that most of the light in this particular image we are just looking at is down here in the darker part of the image, and it's tailing off. And this is the very brightest part, and you can see there's nothing up in this area. And if you're taking pictures, you don't want anything, you don't want this diagram to extend way up here, because what that means is you're blowing out. You have detail that is saturated in 100% brightness. And so you want a histogram that looks something like this, maybe spread out a little bit more, but you don't want to see the histogram flat, and which means that there's a lot of detail that you can't see. Well, this is just, and when I move this cursor, like now, I'm looking at it, I'm changing the effective illumination of the image, and now I'm just looking at the brightest part of the image, and I'm not looking at but again, this is the challenge of taking pictures, is to somehow make an image that will show the darkest stuff, but also the brightest stuff without losing the detail in either. And that's most of the challenge. And that's a challenge for terrestrial pictures too, because if anyone, you try to take a picture of a sunlit day with clouds and shadows, it's really difficult to get the detail in the shadows and the sun in the clouds at the same time, because they're very different brightness levels. And so one of the arts of photography is to somehow being able to figure out how to do that. And in these pictures, there's something called nonlinear stretching. And so we dim the brightest stuff and we brighten the dimmest stuff, so that we get it all in a frame of reference that we can see at once. Anyway, that's probably more information than you really wanted to know, but there it is. Okay, so now we're going to look at, I think I moved the telescope to a different object, and now we'll take another picture of a cluster that doesn't look quite so detailed as the one we were just looking at. This is still considered a globular, but it has a much more open feel to it. So you can see as I zoom in on the brightness, see, there it is. So I think this is still considered a globular cluster, but it's not as symmetrical as the one we were just looking at. There's also, you can see some structure in it. I mean, you can see some lines of stars here, all of these. There's a horizontal line through here. All of this is in the same. See, that's one of the tricky things, is that stars out here have no relationship to this. They could be at a totally different distance from us than this cluster is, and they could be much closer, much further away. We just don't know. But we do know that this group of stars here are pretty much in the same general area of the sky. But that's some of the mystery that has been solved in the last 100 years as to how to figure out what the distances are to these objects. Now we're going to go, I think, to the most famous of the globular clusters. called the Great Hercules cluster. And we'll do that. And then we're going to move on to some galaxies.
So these globular clusters are quite a bit farther away than the nebula we were looking at earlier. As we mentioned earlier, these are up in the upper and lower halos of the galaxy. And so we're talking about 15 to 20,000 light years away for all these globular clusters. And the next one is no exception to that. The Hercules globular cluster is about 25,000 light years away. So way up above the disk of the galaxy. And as Mike was saying, this is probably one of the most famous globular clusters because of how bright it is. You can actually just see this one with the unaided eye on a really dark moonless night.
So I'm changing the screen now. We're looking back at the screen that controls the computer or the telescope we're pointing. So what we were just looking at is down here. Here's the Milky Way through this level of nebula. Yeah, all these green things are essentially mark the Milky Way. And we were looking in this area before. M4, which we just looked at, is outside the disk of the Milky Way. Now we're going to look up here. This is way outside the disk. Here's the disk of the Milky Way, and we're going to be looking up here. So now I'm going to tell the telescope to go there, and now it's going to do that. All these numbers, by the way, on this are all different objects in the sky that have been identified by various people and over the eons. And the M designation, like M13, is offered a person called Messier, Charles Messier, who observed 110 objects in the 1700s. And his catalog is probably the most famous catalog of what are called deep space objects that are further away than anything in our solar system. Okay, so we've done that. We're now going to go back to the camera, and we're going to take a picture of this. And this is
the cool thing about the Messier catalog that Mike just mentioned is that these 110 objects are actually the junk objects, according to Messier. He was hunting for comets. So he wanted to see fuzzy spots in the sky that moved relative to the background stars from night to night. These 110 objects didn't do that. They were all the objects that he knew that weren't comets. But he's more well known for these 110 objects than the several comets that he ended up discovering over the years.
so this is the great Hercules cluster, and I was changing the brightness, so like at this area where you can see the detail in the center, one X marks the spot. So this is a feature of this cluster that has this X. It's just a random group of stars, but when you say the X never marks a spot, well, here's one that does. Marks the center of this one. But as I change the brightness by looking at the dimmer objects, you can see the outer parts of this galaxy, of this cluster emerge.
And this one's huge. It's got about 300,000 stars in it.
Yeah, this one is a very nice object to look through an eyepiece. You can actually see a lot of this. You don't. These clusters are great things to look at with your own eye through a telescope. Okay, so we're going to change direction here, and we're going to start. Now we're going to leave our Milky Way, and we're going to look at objects that are in that are out there in deeper space that are whole other galaxies. And so we're going to start with probably the most famous one. Well, one that at least is the most attractive to see, and it's called the Whirlpool Galaxy. And I'm going to tell the telescope to do that while we're talking. And
yeah, so now we're leaving the Milky Way galaxy, and instead of looking at objects that are hundreds or thousands of light years away, we're going to start looking at completely different galaxies that are millions to tens to 20 million light years away. So as Mike mentioned, much, much farther away than anything we've seen already tonight.
Yeah, so this is one of the most famous, and there it is. This is called the Whirlpool Galaxy. It's about 25 million light years away. So you have to understand what this means. It means that the light that left this galaxy left 25 million years ago. So what we're looking at is what it has looked like 25, which is multiple ice ages ago. And this one, actually, there's two galaxies here. There's this little guy and there's this bigger guy. Is this bright enough?
I was just going to say, if you slide the histogram a little bit, there you go, right there.
Okay, yeah. Yeah, these bright lines are artifacts in the camera. And when you take pictures, these artifacts are taken out. But we're looking at this and we're seeing some of the camera defects. But anyway, so this is a galaxy that is gravitationally bound to this galaxy. And they actually are rotating. This one's rotating around this one. And eventually they'll totally merge. And just as a point of reference, our galaxy, the Milky Way, is in a group of about 30 other galaxies that are gravitationally bound to it. And eventually we're all going to be merged into a single galaxy. But the nearest term thing that's going to happen is about 4 billion years from now, just about when the sun winks out, we're going to merge with the Andromeda Galaxy and form this super monstrous galaxy. So eventually, all these galaxies are coalescing. But this one, I should explain a little bit of the detail what's going on here. These spiral arms are the arms where stars are being formed in this galaxy. Now, all these stars that are out here are in the Milky Way. They're not in this galaxy. But these fuzzy areas like here are actually clusters of millions of stars in this other galaxy. We can't actually see individual stars. The Hubble telescope can image stars in some of these galaxies, individual stars, but my telescope can't. And it looks like we're looking at stars in this galaxy, but we aren't. Like this is not a star in this galaxy. This is a star that's in the Milky Way that just happens to be in the way. And in these areas where these circular arms are, this is called a spiral galaxy, are where all of the stars are being formed in these galaxies. And that's true in the Milky Way. The Milky Way has a well-defined, is a spiral galaxy and has a well-defined set of arms, much like these.
Mike, do you want to blow that image up so we can see a bit more detail, or maybe even go full screen if you want?
Yeah, yeah, this is probably the most impressive galaxy we're going to see here. And that's a little better. Yeah, I think if I go 200%, it's not going to actually help it. Well, because it gets fuzzy, too fuzzy.
That's not bad, actually.
You like that? Okay.
Yeah, that's pretty cool.
Okay. Yeah.
Yeah, you can really see the spiral structure there. Yeah, so the Milky Way probably doesn't look that dissimilar from the larger of those two galaxies.
Yeah, we don't have one of these guys, but yeah, it does look something. And none of these galaxies, by definition, are edge on like this. We're looking face on at this galaxy. There's no reason why this galaxy has to be face on from our point of view, but it is. And a bunch of others aren't. And you'll see them edge on, where you'll see this plane of, like we were describing, the Milky Way is this plane of stars and arms with a bulge in the middle. Well, in this case, we're seeing the bulge in the middle would be right here, but we're looking at it face on, not on plane on. In fact,
Maybe
the
let's,
next one we'll look at will be more plane on.
Yeah, I was just going to say, let's go take a look at the Cigar Galaxy so we can see that.
See that? Yeah, yeah. And okay, so I'm going to go to, and that one's called M82. I hate the name of this thing, but it is what it is. The telescope is moving towards there.
So as we're going there, I'll tell you a little bit about this object. So Mike mentioned its distance, 25 million light years. This one has about 200 billion stars. So roughly the same size as the Milky Way, maybe a little bit smaller, maybe a little bit bigger. We're not totally sure the exact number of stars in our galaxy, but in the several hundreds of billions.
All right, well, we're taking a picture of this guy. This one is actually a pair of gravitational bound galaxies. We're only going to be looking at the smaller one tonight. But there it is. And I'm going to give it a little change. I don't want this graph at all. What happened to mine? There. I don't want this one either.
It was just, yeah, there you go. Yeah, it's just over on the right.
It's buried somewhere. I see it. It's underneath. Okay, there it is. Okay.
So we had a question about, oh, go ahead, Mike.
No, you go ahead. But as Samuel was saying, this is we're looking at a galaxy that's essentially edge on here. I'll dim the bright so you can see the detail in the brightest part, and then I'll brighten it up so you can see the outer regions of it and better.
So we had a question about whether all galaxies are flat and disc-like. Only about half of them are. The other half are spherical galaxies. We call them elliptical galaxies, and they're these big hornets' nests of stars that have a common gravitational center, still occupied by a supermassive black hole, but the stars aren't ordered nicely into spiral arms. They're just orbiting more chaotically. And the biggest galaxies in the universe are these spherical galaxies. The current thinking is that when you have at least two spiral galaxies merged together, the spiral arms get ripped apart and you end up with a larger elliptical galaxy. And that will be the fate of the Milky Way as we merge with the Andromeda Galaxy in roughly 3 to 4 billion years from now.
Right. Yeah, this one, if you see a picture of it, if you've seen any, if you go on to Wyoming Stargazing website or my website, which is earthandskyimaging.com, you'll see this image, and it has big flares of red light out here. And these are this is called the Starburst Galaxy, and it's ripping hydrogen gas from a larger galaxy, which is off in that direction. And this hydrogen gas is being excited by the stars in the area, and it's just emitting all this light, also creating lots of new stars in the process. But this image doesn't show that because it's just too dim without taking a really long picture. Many of my pictures, like I showed you, the Whirlpool Galaxy, my picture of the Whirlpool Galaxy, which you can see on either the Wyoming Stargazing site or earthandskyimaging.com, was 50 hours of imaging, 50 hours of imaging to get all the detail that you can see here. We're looking at an image here that's 20 seconds. But if you want to really see all the detail in this one probably would be, 15 hours, 20 hours of imaging to really get the detail in all of this. Okay, so I think we've done most of the agenda. We're saving the comet. And,
Well, I think we might want to move on to it so it doesn't get any lower in the sky.
yeah, and also, so because I think that was one of the features. So I'm going to shift to we're going to shift from the 20-inch telescope, which is on one. Yeah, I have a different computer controlling each of my telescopes. So I'm now going to move onto a different computer, which means it's controlling a different telescope. And so I'm going to share my screen on this telescope. And actually, you're now seeing a picture of the comet.
We're not seeing that yet, Mike.
Oh, you're not? Okay.
No, you have to share a different screen.
Yeah. Okay, maybe I'll stop sharing this one on this computer.
There you go.
Okay, you're not. Okay, this is a picture we probably took over an hour ago. I'm going to take a new picture right now of this, and we'll see. I was actually taking pictures of this the other night when it was at midnight, and yeah, well, we're getting there, but it's rising higher in the sky every night. So, okay, so I gotta. All right, we're not seeing it. Where is it? I may have to repoint this thing.
So as Mike does that, I'll tell you a little bit about this comet. So all comets, including this one, are basically the leftover stuff from the formation of the solar system. After the sun formed, there were huge debris fields of small chunks of rock and clouds of dust and gas. And most of that stuff, just because of gravity, clumped together and formed the planets. But there were billions of smaller pieces of debris that didn't form into the planets, mostly at the outer edges of the solar system. And those are the comets. So some of them, the short period comets like Halley's Comet, come from an area called the Kuiper Belt, basically an area about 100 times farther away from the sun as the Earth is. This comet, Comet Neowise, and long period comets probably originate from an area much, much farther away called the Oort cloud, this huge spherical shell of debris left over from the formation of the solar system, which is as much as a light year away. So this comet is believed to have an orbital period of, I think it's about 6,800 years. So it takes a long time to complete one trip around the sun. And so it won't be back for quite a while. And the nice tail that we saw in that last image that Mike had up is similar to all the tails that comets grow when they get close to the sun. When they're far away from the sun, out either in the Kuiper Belt or the Oort cloud, they're just chunks of an ice-covered rock. It's only when they approach the sun and are warmed by solar radiation that dust, gas, and ice gets sublimated, changed from a solid straight into a gas without liquefying in the vacuum of space. And that's what forms the tails of comets, which can extend for hundreds of thousands of miles behind the nucleus of the comet, the actual rocky part. And so this comet in particular has an incredibly long tail, and that's what's kind of been dazzling people as we've seen it grow in brightness over the last several weeks, first in the early morning hours and now in the evening hours. And so it's probably the brightest naked eye comet that we've had in the Northern Hemisphere in the past decade. So it could be quite a while before we have one like this again. So if you haven't had a chance to take a step out around this time of night and take a look at it, you really should. It's just underneath the Big Dipper. in the western horizon this time of night. So if you can find the Big Dipper, just go straight down towards the horizon from there, and just a couple of finger lengths, your index finger held out at arm's length, a couple of those up above the horizon, you should see this kind of big glowing object, which then gets diffuse as you look away from the brightest part of it.
Yeah, so
Any luck in finding it?
I'm not seeing it, and I don't understand it. Let me-
Somebody asked how big comets are. So they're on the order of hundreds of meters to a couple miles across. So they're big chunks of rock. I think this one is about 300 meters across. A big chunk. The one that hit the Earth and probably led to the demise of the dinosaurs was quite a bit bigger. That one was probably on the order of 50 miles across. So this one's quite a bit smaller than that, but still, it's a big chunk of rock. I think the average is about 1 to 2 miles in diameter. That's just the chunk of rock. That's the nucleus of the comet. You can't actually see that when it gets close to the sun. All we see is what's called the coma, the fuzzy halo around the comet from all the sublimating material. And so, yeah, these objects that either come from the Kuiper belt or the Oort cloud get jostled by other objects out there. And one or the other gets jostled in towards the center of the solar system, and the sun's gravity does the rest. And that's why these comets have long extended elliptical orbits compared to the more or less circular orbits that planets have. And so another reason why these things take so long to complete an orbit around the sun. Their orbits are really stretched out compared to the orbits of planets that formed much closer in towards the sun and have nice, tight, locked circular orbits compared to these much longer ones that comets have. So Mike, maybe we'll just we'll show some of the pictures that that we've taken over the last couple of days. You're muted now. We can't hear you. Still muted, Mike. So as Mike tries to hunt down the comet for us here, I'll share my screen and show you some of the pictures that I've taken from a couple nights ago, and then we'll see if we can find the planets and wrap things up for the evening. Bring up my pictures here. So here's a close-up of the comet that I took a couple nights ago, and you can see that there are two distinct tails. There's kind of a yellowish, thick, diffuse tail, and then a much thinner blue tail coming off at a different angle. And most comets do have two different tails, the brighter of which is typically a tail made up of dust particles, which are reflecting sunlight, and another, the thinner tail, that's made up of gas. And they typically go off in different directions like this. The dust tail usually follows right behind the path of the comet. So as the comet is orbiting around the sun, the dust tail moves in the opposite direction, just trailing behind, directly behind the comet. Whereas the gas tail gets pushed off a little bit by interactions with charged particles from the sun. And so the angle is usually, I think, between like 15 and 20 degrees off, trailing off to the side of the direction the comet is actually moving. And so the colors are hard to pick up. This is just a 30-second exposure. Had I done lots of these exposures and stacked them together like Mike does with his astrophotography work, you'd actually see a nicer variation between the color here. But I think you can make out the difference between the two tails. Took a couple other images zoomed out. Here's one that just kind of shows you the position of the comet relative to the Tetons, and kind of the classic silhouette of the Tetons there, with the comet setting in the west a couple nights ago. And then one other earlier in the evening, there was still a lot of light in the sky, and so the blue the sky came up in this shot that I took a much lower zoom on the comet. Mike, were you able to find it? You're still muted. So any questions about the stuff we've looked at tonight, or specifically about the comet? Hopefully we'll have a chance to try to check out the planets before we wrap things up, but happy to take any questions. You can either type them into the chat, or you can just unmute yourself and go ahead and ask your questions.
Hi, Sam. This is Deb.
Hey, Deb.
Hi.
How you doing?
I would love, maybe not tonight, or if you have time tonight or whatever, what are the planets that are currently visible that are a little closer in our world, even though they seem so benign compared to everything we saw tonight?
Yeah, so
Things that I
Jupiter-
can go out and look at.
Yeah, so Jupiter and Saturn are making a really nice showing the opposite side of the sky as the comet. They're low in the southeast right now. And Jupiter just made its closest approach to Earth. I think it was just yesterday or the day before.
Oh, no way.
It's really beautiful in even a small telescope like the one you have. If you point that towards Jupiter, you'll see the cloud bands and the 4 largest moons pretty easily.
Cool.
Yeah, so it's really lovely. Saturn is twice as far away. Jupiter is about 500 million miles away. 30 light minutes. Traveling at the speed of light, you get there in 30 minutes. Saturn's twice as far away at about 1 light hour, or about 1 billion miles. But the rings are turned at a really nice angle right now with respect to the Earth. So you can clearly see the ring system of Saturn and its largest moons as well. So even with a pair of good binoculars, you can just make out the rings of Saturn right now. So definitely worth checking out. And yeah, same with Jupiter. You can see the cloud bands with a good pair of binoculars as well.
Great.
Thanks for asking. How are we looking, Mike? You're still muted. Still muted, Mike. We can't hear you.
It's like he's not on our list. He's not participating. Seriously, like if I pull down my participants list, I don't see him.
Oh, I can see him. He's there.
I see his face, but he's not on the list.
Can you hear me now?
Oh, there he is.
Now we can hear you, Mike.
Yeah, okay. All right. Yeah, just to show a screen. This is a picture I took the other night, by the way. I'm going to try with my other telescope to do this again. I have a feeling I know what happened. I think the 20-inch telescope is blocking the view of the 6-inch telescope. And we just happen to be, I'm going to try to take another picture and see if I can find it again. But my 20-inch telescope is sort of out of commission at the moment. So we're probably done for the evening with that one. But let me just see if the 6-inch will, the 20-inch has moved away and I can see something with the 6-inch.
Would it be worth trying to go for one of the planets since it's so bright?
No, it's not making any difference. Well, no, I now have, I've now, without me going outside and restarting my 20-inch, somehow the telescope is not functioning at the moment. So I'm kind of out of pocket here. The only thing I can do, did you see the picture I took the other night? Did I show you that?
Yeah.
Okay, you saw that. All right, so that's about all we can do. I could show some other pictures, but I think, unfortunately, for some reason, I'm not seeing the comet right now with my 6-inch telescope. And
Would it be worth trying to point the 6-inch to the other part of the sky to try to see one of the planets?
Yeah, I can try. Yeah, let me just point it at something else. Let me try pointing it at Jupiter, for that matter. And I'm going to point the 6-inch telescope towards Jupiter.
I think you might be covering up your microphone, Mike. It's a little muffled.
Okay.
There you go.
All right. Yeah, I'm working at 2 different telescopes. So, all right. Well, let's see what happens if I take this picture. Well, too long an exposure, but that's okay. Let's just see what happens. Well, okay. Seeing lots of stuff here. But, not seeing Jupiter. Oh, well. I think we're out of business here. I'm sorry, Samuel. I think,
All right.
okay. I think we're going to have to call it quits tonight.
Sounds good. We saw a lot of cool stuff. Well, everybody, thanks so much for joining us this evening. Weather permitting, we'll definitely do this again soon. And as we progress into the summer, we can take a look at some different objects. So, yeah, thanks so much for joining us, and have a great evening.